In this video, I'm going to talk about the third and the final definition of extreme values, and it's known as the definition 3. Definition 3 of extreme values. Right. So this is definition Definition 3. So according to this definition, you don't pick the largest data point, which is this one, but you pick the first few largest. So you pick the second largest, the third largest, the fourth largest, and the fifth largest. So according to this definition, the extreme values are the first few largest data values. Okay. Alright, so this is a variation on the definition 1. Remember, in definition 1 we picked only the largest, but here we picked the first few largest. Right? Alright. Okay. Now what I'm going to in the two definitions I've looked at so far, in each case I looked at the distribution of extreme values as n is the sample size here approaches infinity. So I'm going to do something similar over here. Okay. Before I do that, let me look at. Let me introduce some notation, right? So the notation will be as follows. Let this one denote the largest data volume. Right? Let M2 denote the second largest data volume, right? And let Mn3 denote the third largest data values, and so on until, suppose we pick R largest observations. So this denotes the rth largest data volume, right? So so in the picture that I showed you previously, your R is equal to 5. Okay. So the question is, what is the distribution of this as n approaches infinity? Now you may recall that we asked a similar question with respect to definition 1 and with respect to definition 2. Right? So now the answer, I'm going to just state the answer without giving you proof or anything like that. I don't expect you to know the proof. There is a result. A result due to Weizmann 1978, which says the following. It says that the joint probability that the joint probability of this events where an and bn are the numbing constant that we talked about in definition 1, right? Approaches the following. Just bear with me. Right? So that the multiple sum of the following, gamma 2 minus gamma 1 to the power s1 divided by s1 factorial, then gamma r minus gamma r minus 1 to the power s r minus 1 divided by s r minus 1 factorial times e minus gamma r. Alright? Okay, as n approaches infinity. So it is a complicated expression, as you can see, and that's why I don't expect you to know the proof. Where gamma I is 1 plus An is the same as in the extremal types theorem. Okay, and your Bn is also same as in the extremal types theorem. All right. So this is the result. The result I will call star for later use is the analog of what we saw for definitions 1 and 2. So it basically gives you the limiting distribution of the R largest data values as n approaches infinity. Okay. All right, the next question is how are we going to use star in order to model the data in this case being all largest data points every year, right? Now it can be shown from star that the joint PDF right? So the joint PDF of the all largest data values is given by the following expression. Right, where x1 corresponds to the largest of the data points, x2 corresponds to the second largest, and so on until xr corresponds to the rth largest, right? Okay, and so this is, once again, I don't expect you to know the proof of this. So what I have shown here is that the star, which I mentioned in the previous slide, can be used to derive the joint PDF of the R largest data point, and is given by this. Okay. All right. Now, in the next page, I'm going to talk about estimation under definition 3. In other words, how can we use what we have learned so far to estimate extreme values under definition 3. Okay. Now suppose you have the following data. So these are the R largest data points from one particular year, which I call just the first year. All right? And suppose suppose this is the R largest data points from the second year of data. So remember, each year you're picking the R largest data values, and so on. And suppose this is the R largest data values from the Tth year. So capital T could be 10, 100, 1000, 10,000, or whatever. Okay. So just what I have written is the following: the data are So the data I have written down are the R largest data values for capital T years. All right. So from the joint PDF that I have written down in the previous page, I should now be able to write down the likelihood function. So the likelihood function is as follows. It's going to have three parameters: mu, sigma, and psi. Right? It's going to be all right. So you see how I got this. This is the joint PDF I had mentioned in my previous page. So it's basically the product of this over the capital T years. Each year has R largest data points. Now you can, of course, you can simplify this. If you simplify this, you get sigma Alright, so this is the simplified form of the likelihood function. Right? The next step is to take the log of the likelihood. Right? So that's what I'm going to do now. Right? So you should take the log of the likelihood, which I wrote in the previous slide. This is what you will get, capital T or log of sigma minus okay. So this is the log of the likelihood. Right, and so the MLEs of the three parameters, mu, sigma, and psi, are the simultaneous solutions of the following three equations. So you take the partial derivative with respect to mu, set that to 0. You take the partial derivative with respect to sigma and set that to 0. And you take the partial derivative with respect to psi and you set that to 0. So the solutions of these three equations will give you the maximum likelihood estimates of the extreme values under definition 3. Okay. Okay, now just to finish off, I have worked out the partial derivatives myself. So this is the partial derivative with respect to mu, and this is the partial derivative with respect to sigma, and this is the partial derivative with respect to psi. So once again, the MLEs of so the MLEs of the three parameters are the simultaneous solutions of equation 1, 2, and 3. Alright. Okay. Alright, so this completes the video on definition 3 of extreme value. It also completes the three definitions giving the three different definitions of extreme values. In the next video, I shall start a new topic, which is called portfolio theory. Because so far everything we talked about is about extreme values. Remember, at the beginning of the course, I said there are two parts to this course: extreme values and financial risk. So in the next video, I shall make a beginning on the second part of the course, which is about financial risk. Okay.